All right, so here we are again at the fish problem. We have a 6 kilogram fish swimming 1 meter per second, swallows a 2 kilogram big fish, not a big fish, but a fish that's a rest. Find the velocity of the fish immediately after lunch. Okay, so the system is going to be both fishes. Okay, so we'll look at the net momentum before and after lunch. So if we start out, we have a big fish over here. We have a little fish over here. So whatever momentum we have to start with has to be the same at the end if we call both fish together the system. Okay? So what happens on this side, you may notice that they've actually added the masses together. You might say, hey, why'd they add the masses together? Well, remember, the big fish is eating the small fish, so they're going to go at the same velocity afterwards. So we have a 6 kilogram big fish going at 1 meter per second, a little fish, third the mass, not doing anything. So momentum to start with is 6. The momentum we end with is also going to be 6. But we have a little bit greater mass. That means the fish is going to be going a little bit slower. So if you solve for the v, now we have a slightly greater mass than we started with. The speed is a little bit lower just as we predict. Okay, there we go. Speed is just a little bit lower just as we predicted because we're gaining more mass, but we indeed have the same momentum before. And there's the big fish. Oh, blood in the water. Look at that. Let's see that one again. Okay. So we have a speed of 3/4 meter per second. Big fish, little fish. So the momentum before that lunch was 6 kilogram meters per second of momentum. That's the momentum we have afterwards. So even though we have 8 kilograms times v, that would have to be still 6 kilogram meters per second because that's the momentum we started with. Okay, so remember we're making both fish part of our system. Okay, if you made it a smaller system of each fish, well, now we have an impulse because you got an impulse on the little fish, accelerating it up to 3/4 meter per second, and you have a deceleration of the big fish by about 1/4 meter per second. But it's much easier to find solutions to this if you're looking at the systems together. So there aren't any, so any big fish hitting little fish, that's an internal force if this is the whole system, and that's why you can have the same momentum before and afterwards. Hey, what if you have a 6 kilogram fish swimming at 1 meter per second, swallows a 2 kilogram fish that's going at it at 2 meters per second? Well, that's a 6 on the momentum in one direction. That is a 2 times 2, a 4 kilogram meters per second in the other direction. Dios mío, what's the net momentum of the whole system? Well, look at before and afterwards, and so here we go. Big fish, little fish, same story. This is still a 6, but this is a -4. A lot of people forget to put a negative. Guys, these are vectors. You absolutely have to have a negative showing one is going the other direction. Okay? So if a 6 plus a -4 is 2, that means we have a net momentum of 2, but that's an 8 kilograms. So solving for the velocity, it's going to be much slower now because the other fish has some momentum going the other direction. Oops, I had the directions wrong. They're going the opposite direction. But the point is, you'll notice the big fish is going slower, but he slows down a little bit. Okay? Well, not a little bit, quite a bit, because it was going 1 meter per second. It slows clear down to 1/4 meter per second after the chumming. Alrighty. Hey, let's get even crazier. Now we got a 6 kilogram still going to 1 meter per second, but now the other fish is going at 3. So how does the momentum compare to each other? Well, you have the same momentum, but opposite directions. So what's the momentum beforehand? Well, the momentum beforehand is actually 0. So what does the momentum afterwards have to be? Also 0. If we consider both fish part of our system, we have to have the same momentum before and afterwards. So there's a little fish going fast. Oh, in your face, big fish. In your face. So, but you notice, what's the momentum here? Still 0. Even though little fish ate big fish, the total momentum is still 0 because there was no net momentum before the collision and there wasn't afterwards as well. So, pop quiz. Was this an elastic or inelastic collision? Well, they both had kinetic energy before. Do they have any kinetic energy afterwards? Now remember, you don't have a negative kinetic energy because it's non-directional, because you're going to square the 3. So if you square the 3, in fact, let me pop quiz you this. Which fish even though it had the same momentum opposite direction. Which one had the greater kinetic energy? Waiting. It, in fact, was the little fish. Because if you go 1/2 mv squared, 1/2 of the mass is 3 times that squared. 3 times 1 is 1 joule of kinetic energy of the big fish going this way. But the little fish had a 1/2 of the 2, which is a 1. But it's 3 squared of 9 joules. It's got 9 times the energy. So it actually had 9 times the kinetic energy that the other fish had. So, but clearly, total energy, you got a 1 over here and a 9. That's a total of 10 joules of energy to start with. There's absolutely no energy left over. So what happened to all 10 joules of that energy that's going, because the fish isn't doing anything, there's no kinetic energy. Well, when things smack together, whether it's big car, little car, or whatever, it gets a little warm afterwards. So that 10 joules have gone into heat energy, maybe even warmed up the fish for the little fish there a little bit, who knows. But so the energy is still technically still there, it's just not a mechanical energy, it's in thermal energy. But there was no net momentum, for considering both fishes, there was no net momentum beforehand, there can't be any momentum afterwards since we didn't have any external forces acting on those two fish. So that's why the fish doesn't go anywhere, okay? But the kinetic energy is clearly way different than the start of it. That's why this is an inelastic collision. Alrighty, so now the 6 kilograms still going at 1 swallows a 2 kilogram going at it at 4 meters per second squared. Dios mío, now the little fish has more momentum and way more kinetic energy. What's going to happen when they collide? Oh, that's going to be a tummy ache for later, huh? Look at that. So the net momentum was greater to the right because the little fish not only had more kinetic energy, way more kinetic energy, but also had more momentum. So pop quiz, let's say little car versus big car. Which would you rather be? Would you rather be that little car screaming like that or the big car that's going backwards? Well, if you do the math, it is the same impulse on both, but the change in velocity for the big fish was much smaller than the change in velocity of the little car. Hence, between collisions between car, it's always safer to be in the bigger car because you have a smaller change in velocity. The little car has all kinds of energy and loses almost all of that. It has a little kinetic energy left over, but in both of these cases, lost a tremendous amount of kinetic energy, which is going to do a lot of work on stopping the people. So it is the same momentum before and afterwards, but not the same kinetic energy. We have way more kinetic energy here than there is afterwards because even though there is some kinetic energy left over, they're going so slow, it's hardly any kinetic energy left over. All of these examples of fish chomping on other fish, they're all non-elastic collisions. All right, so quick thing on the vectors. So in reality, now you have two cars coming together, bam! Well, that's the momentum you have before has to be the same momentum as afterwards. Okay? So in the setup, we have this momentum plus this momentum. Well, if you add those two vectors together, that goes right there. That's where the cars go. Now, if that's an inelastic collision, both cars will travel because they stick together and they'll go this direction. If it's a more of an elastic collision, they can still bounce off of each other, but still the momentum you have afterwards of each car is going to be the same as the momentum that you had to start with. You're always going to have the same momentum. So this is not only the momentum after the collision, that was also the momentum before the collision right at this spot right here. If we add those two vectors together, we have the same momentum beforewards and afterwards, whether it's inelastic or not. Okay, but if they stick, it's going to be an inelastic collision. So the momentum of the car before is the same as the momentum afterwards, doing your little math there. Another quick example. If we have a firecracker, a kaboom going on. So it's got momentum going that way. There it is, kaboom. And you notice the pieces fly everywhere, but the net motion of all the pieces still go in this direction. Even if pieces not only go there and there, they go in every single direction when there's a blow up. The center of mass of that whole thing still moves in the same direction because that boom was an internal force. So the whole thing would still go in that same direction. The center of mass would still go in that same direction. Okay? Same for subatomic particles. When they crash together, whatever momentum you have. So you have two protons going at equally high speeds towards each other. There's actually no momentum before the collision. they smack and stuff goes everywhere. There's actually no momentum after the collision either. Okay? And since those are elastic collisions, you also have whatever energy you started with, you have energy in the end as well. Well, in all cases. So sometimes you get these paths like this. Things are twirling in a magnetic field, some charged particles and so on. But you still have to have the same energy before and afterwards. But that's all, folks. So be some other videos about this momentum stuff coming up, and find some kind of a lab-like activity for you guys to do. Have a wonderful day and week.